MVCC or multi-version concurrency control. The core idea of MVCC is to store multiple versions of each data item in the database, allowing read operations to access these versions without acquiring locks. This enables read operations to proceed even with write operations are in progress, thereby enhancing the concurrency performance of the system. Hello everyone and welcome. My name is Gordon and I'm a senior software engineer. Over the next few minutes, we will explore what MVCC is, why it's crucial for high-performance databases, and how it works. Let's get started. Here is the roadmap of our discussion today. We will start by defining what MVCC is and its core ideas. Then we will look at the problems itself, particularly the pain points of traditional concurrency control. Next, we will dive into the core principles, focusing on hidden fields and the read-view mechanism. We will also see how MVCC behaves different under various transaction isolation levels. Finally, we will summarize its key advantages. This structure will guide us from the what to the why and how. So, what exactly is MVCC? Simply put, it stands for Multi-Version Concurrency Control. It's the ingenious technology InnoDB uses to handle multiple transactions accessing the same data simultaneously without locking everything up. The magic lies in three key principles. First, read operations. Don't block each other or write operations. Second, write operations only lock the specific rows they need to change. And third, this allows for true concurrent reads and writes without neutral blocking. MVCC achieves lock-free reads under concurrency by saving historical versions of data, solving dirty reads, non-repeatable reads, and phantom reads. To understand why MVCC is so important, let's look at the alternative, traditional locking mechanisms. Without MVCC, databases rely on read-write mutual exclusion to ensure data consistency and transaction isolation. Read locks prevent other transactions from modifying data while it's being read, and write locks prevent both reading and writing while a transaction updates data. This prevents issues like dirty reads, where a transaction might read incomplete or incommit data and lost updates, where concurrent modifications could lead to data corruption. By enforcing mutual exclusion, the database ensures that transactions operate in isolation, preserving the integrity and correctness of the data. However, this comes at the cost of concurrency. Locking prevents multiple transactions from accessing the same data simultaneously, leading to performance bottlenecks in high-traffic environments. Now, look at MVCC's solution on the right. MVCC addresses this by allowing multiple versions of data, improving concurrency without sacrificing concurrency and isolation. It enables read-write non-blocking, significantly boosts concurrency performance through lock-free reads, and provides strong transaction isolation. This direct comparison highlights why MVCC is the cornerstone of InnoDB's high concurrency capabilities. Let's now explore the core principles. Imagine each row of data has a time capsule. This is the version chain. InnoDB keeps multiple historical versions of each row. When a transaction reads data, it doesn't just grab the latest version. Instead, it uses a set of rules embodied in read view to determine which version it can see. Think of it like everyone wearing a pair of history glasses. You can only see the world as it was when you put them on. Similarly, MVCC gives each transaction a consistent snapshot, ensuring it only sees data committed before the transaction started, providing a stable and predictable view of the database. To implement this versioning, InnoDB adds 3 hidden fields to each row. DB tracks ID makes the transaction that created or updated the row. DB row point is a pointer to the previous version in the undo log. DB row ID is a hidden primary key if no primary key is defined. Let's walk through the concurrent example on the right to see how these components work together. This example demonstrates the life cycle of the single row of data through 3 steps: an initial insert and 2 subsequent updates. Step 1. Initial insert by transaction 100. We start with a simple insert statement. When this happens, InnoDB creates a new row. This DB tracks ID for this row is set to 100. This ID of the transaction that created it. Since it's the first version, the DB row pointer is none, and there's nothing in the undo log yet. Step 2. First update by transaction 101. Now a second transaction comes in and updates the row. Instead of overwrite the existing data, InnoDB creates a brand new version of the row. The current row DB tracks ID is updated to 101, and its DB row point now points to a new record in the undo log. Let's call it version 1. This undo log record version 1 preserves the previous state of row with its DB tracks ID of 100 and its original date Alice. Step 3. The second update by transaction 102. A third transaction ups the row again. The process repeats. A new version is created. The current row DB tracks ID becomes 102, and its DB row pointer points to a new undo log record version 2. This new record version 2 stores the state from the transaction 101, and crucially, its own DB row pointer points back to version 1. This example perfectly illustrates how the undo log acts as a history storage, and the DB row pointer acts as a chain link, connecting the current version to all its historical predecessors, forming the version chain that is essential for MVCC. The history classes I mentioned earlier are formally known as the read view or consistent read view. It's created when a transaction starts its first read and acts as a data snapshot. This read view is crucial because it defines the entire universe of the data that the transaction can see from its entire duration. A read view is essential data structure that contains 4 key pieces of information which we can see on the screen. First, MIDs, the active transaction ID list. This is the list of all transaction IDs that were active and uncommitted at the moment the read view was created. It helps the database quickly check if a date version was modified by another transaction that hasn't finished yet. Second, mini transaction ID, the minimal active ID. This is the smallest transaction ID from the MIDs list. Any date version created by a transaction with an ID smaller than this value is guaranteed to have been committed before our transaction started, making it safe and visible to us. Third, the max transaction ID. The next transaction ID. This is the next ID that the system is going to assign to a new transaction. Any data version with a transaction ID greater than or equal to this value are created after our snapshot was taken, making it a future date that we cannot see. Finally, create trans ID, the current transaction ID. This is simply the ID of our own transaction. is used to check if a data version was created, the transaction itself, which is always visible. Together, these four values form the rulebook that a database uses to determine which versions of data are visible to your transaction, ensuring consistency and isolation. But how does the read view determine visibility? When a transaction reads data, it starts from the latest version and follows the version chain down, judging visibility according to the following rules. First, if the version was created by the transaction itself, it's visible. Second, if the version's transaction ID is less than the minimal active ID, it means that the transaction has already committed, so the version is visible. Third, if the ID is greater or equal to the next transaction ID, it's from the future and invisible. Finally, if the ID is in the list of active transaction IDs, it's uncommitted and invisible. If a version isn't visible, the database follows the rollback pointer to check the next historical version, continuing until it finds a visible one or reaches the end of the chain. The behavior of MVCC changes based on the transaction isolation level, specifically when the read view is generated. In read committed mode, a new read view is created for every select statement. This means you can see changes committed by other transactions during your transaction, which can lead to non-repeatable reads. In contrast, MySQL's default level repeatable read creates the read view only once at the beginning of the transaction. This ensures a consistent view throughout, solving the non-repeatable read problem and providing a stable snapshot. MVCC is not generated for all CQs. It's important to distinguish between two types of reads in InnoDB: snapshot read and current read. Snapshot read is the normal select query we have been discussing. It's log-free and reads from the version chain via the read view, offering high performance. Current read is the operations like select for update, lock in share mode, update, delete, insert. It always reads the latest committed version of the data and places locks on it. Understanding the difference is key to write high-performance concurrent code. Alright, let's summarize the core advantages of MVCC that every engineer should know. First, lock-free reads drastically improve concurrency. Second, it's a foundation of transaction isolation, ensuring data consistency. Third, the non-blocking nature of read and write operations is a game changer for performance. Finally, MVCC is truly the soul of InnoDB's high concurrency, making it indispensable for model high-throughput applications. Let's do a quick recap in the end. MVCC is multi-version concurrency control exclusive to InnoDB. Its core is the combination of multiple data versions and the read view visibility rules. Its main goals are log-free reads, high concurrency, and strong transaction isolation. Remember, it only applies to normal select statements, which are snapshot reads. And fundamentally, it's the mechanism that implements MySQL's default repeatable read isolation level. Thank you for watching today. See you next time.